Right, I'm happy to introduce our next speaker, Kasia Rejzner, and her title is Quantization of Gauge Theories in Perturbative Algebraic Field Theory.
Okay, thank you very much. Thanks for inviting me to this live meeting. So before I will talk about quantization of gauge theories, I'm going to start with a bit of a commercial break. So yeah, I wanted to advertise to you something that I'm a part of and president of, which is International Association of Mathematical Physics. So some of you might have heard of it. If you haven't, then it's great, so I can tell you. So this is, well, it's a learned society, so it's an association of mathematical physicists, and the aim is to, well, support research in mathematical physics, enable networking, and kind of foster, the growth of the area. So if you are a junior researcher, it might be an opportunity for you to meet people, to look for jobs. We advertise jobs within mathematical physics community on our webpage. And yeah, you can essentially start new things in the areas that you might not expect. If you're a senior academic, then, well, that might be an opportunity for you to support the new generation and take part in making decisions that affect the next generation of mathematical physics. Okay, so yeah, the practical things, it's actually very cheap. It's just 30 euros per year, and the first year is free. So if you're thinking, oh, I don't know, maybe it's for me, maybe it's not, you can still sign up, and after a year you quit. It's like Amazon, you don't have to pay. Yeah, we also organize the International Congress of Mathematical Physics, which is actually happening this year in Strasbourg, starting 1st of July. So if you have a last minute desire to come and join us, please do. All right, so yeah, just, oops, that doesn't really work, but okay. I'm going to use, yeah, no, now it works, okay. So yeah, we organize the Congress. We award various prizes. The biggest one is the Henri Poincaré Prize. So if you want to add something really cool into your CV, it's that. And many other things that also look cool in your CV. We offer financial support to conferences. It's not like huge amount of money, but it's money. Money helps. And we also organize the online seminar. So if nothing of this is of interest, then please at least have a look at our seminar. And you can follow the talks, you can watch them offline later as well. And yeah, please join us. So here is our webpage, here's the QR code for those of you who do those things. And yeah, if you want to find out more, you can talk about it with me later. Okay, so thank you for that. We can switch to the board. So coming back to the actual topic. All right, so quantization of gauge theories, that's actually a big thing in quantum field theory. People want to quantize those, and there is a lot of money actually attached to it. So one of the millennium problems is to quantize Yang-Mills and show that there is a mass gap. If you show there isn't a mass gap, you're not getting the money. So, but then you are spoiling the fun for everybody else. So there is a satisfaction. Apart from this ridiculous amount of money, it is also a really interesting problem, and I think a lot of things that are happening at this conference are somewhat inspired, related, or inspiring for solving this problem. Okay, but I'm actually working in a very particular approach that some of you might have heard about, which is first AQFT. Oh, I don't like that show. And in particular, it's perturbative rendering. So let me say a few words about this approach, what it is, and then I will discuss construction of models. Okay, so let's get started. So first of all, I'm working on a certain class of Lorentzian manifolds. I know that a lot of things here have been Euclidean. I like Lorentzian, which makes my life more difficult. So let's take a Lorentzian manifold M, and I assume it to be globally hyperbolic. which means essentially has a Cauchy surface. The Cauchy surface is a great thing for doing initial value problems. So this is a kind of good manifold for, say, solving wave equations if you like PDEs. Okay, and then the sort of main idea of algebraic quantum field theory is that you can define your theory, your QFT, by assigning algebraic structures to regions of spacetime. So here we consider subsets, embedded subsets, call them O. I draw it as a diamond because this is actually a sort of prototype of a nice subset. So this is supposed to be causally convex. Okay, so it contains all the causal curves that start and finish within it. So there's no causal curve that goes woo outside and goes back. And I want them to be simply connected. So these are sort of like building blocks of my theory. Simply connected. Okay, and the sort of category of all these things together with their embeddings is called cause of M. Okay. And now to these subsets, I want to assign algebras. So I assign to it A of O. Now, what's A of O? Well, that actually depends on whom you ask. So in the original framework, it was designed by Hagen Kasia. And that was, well, the main paper was in 64, a long time ago. They assumed those things to be C-star algebras. Okay, but then it turns out that, well, that is quite rigid, so it's relatively hard to construct models in that setting. So then later on, and well, there were many people related with this. So let me drop some names. Notre, Dutch, Hagen. I'm not mentioning just because they are my friends. They actually came up with this. So they were working on a similar setup, but where these objects are something weaker, so topological star algebras. Okay, and that was much newer, so this was 2000s. So there was nothing happening in between. And then even more recently, there was my work with Hagen, where we weakened this and worked in chain complexes. Oh, I should maybe ask that, well, okay, so these are topological star algebras, but actually form a power series in topological star algebras. And then Hagen, myself, and that was, let's say, 2011, when my thesis came out, and that was chain complexes in Limov. Okay, so as you see, the various choices of the sort of setup, but whatever choice you want to go with, you're interested in constructing this A as a functor. So this is going to be a functor to be appropriate category. Okay, but not just any functor. So there are some axioms that this functor is supposed to satisfy. So I'm going to state those axioms. There are just two that I'm going to actually care about. There are more axioms sort of on the market, but two that I think are important. So axioms.
In da means topological star algebra.
Sorry?
So in chain complexes in means topological.
Topological star algebras. Yes, yes. That's the dot. Yeah. About C star algebras later. Axioms. So the first is causality. Okay, so here is a picture. So if I have a larger diamond and inside it two smaller diamonds, O1, O2, okay, such that these are it's good? No, they're not good. Sorry. No, they're good. Such that they are causally disjoint, so they cannot be connected by a time-like or null curve. So here O1 and O2 causally disjoint. Okay, then I want the corresponding algebras to commute. So the operators here commute with operators there. And this commutator here is in the sense of A of O. So this actually draw it inside this larger region which encompasses both. So this is kind of independence, basic level of independence. There can be more advanced notions of independence of quantum operations, but this is the basic one. And it reflects the fact that quantum field theory is a relativistic theory, so has to be compatible with the causal structure of space-time. So no operation, no information can be faster than light. So that's physics. And then two that's somewhat related to dynamics. It's called the time slice axiom. And here is the picture. So we have, again, a region, and here we intersected with some Cauchy surface. And then we take a neighborhood of that Cauchy surface. I'm going to denote it N, and this larger region is O. We want that the algebra of A of N is quasi-isomorphic to A of O. So this is quasi-iso. And this means that we have some notion of dynamics. So that's a very sort of basic implementation of the fact that in classical theory we would have Cauchy data in the neighborhood of a Cauchy surface, so values of the fields and their derivatives, and then we have well-posed Cauchy problem. We can reconstruct the solution in the whole space. So classically, this is obvious for, say, wave equations. So there's a class of equations where it works. And here, this is a sort of algebraic version of that also is implemented on the quantum level. So everything I need to know about my operators can be localized as close as you want in the polar neighborhood of a Cauchy surface. Okay, so that's all fun. And now, so is this everything? Okay, it's not everything, because if you want physics in the sense of physicists, then you really want to get numbers out of that. So this is algebras. Algebras don't tell you the measurement results. So you need some way to extract numbers from your framework, and this is achieved by the notion of states. So on top of that, you have X. And so for A, topological star algebra. The state is, so state omega is a map from A to C, the complex numbers, such that so on a positive element, so on things of the form A star A, this is non-negative, and this is normalized. So on the identity operator, this gives 1. That's a state. And this, sometimes we just don't talk about that much because, I mean, personally, I'm actually interested in algebraic structures, so I don't come to states very often, but at the end of the day, you need that. And this is one of the reasons why that first sort of formulation with C-star algebras has not been entirely conclusive yet in terms of model production. So yeah, let me now turn to the question of constructing models and discussion of states on those models that are viable. So I guess this is the place to go. Models. So first of all, yeah, so if A goes into C-star algebras, actually there has been progress over those, yeah, more than 50 years. So recently, actually, there was a proposal by Buchholz and Frenhagen how to construct such functors into C-star algebras to describe interacting field theories. Interacting field theories is good. It's much better than free theories because free theories are excessively boring because nothing happens. So we are after interacting field theories. So, okay, that was 2020, Buchholz, Frenhagen. So A as a factor from cos to C-star algebras that describes interacting UFTs. Okay, but there is a caveat. So I mean, we know there are many states of C-star algebras. Okay, states on C-star algebras is not a problem. This is like, you know, functional analysis 101. But again, if you ask a physicist, then you want some distinguished states. You want states that describe some physical situation. And in quantum field theory, people often ask for something called a vacuum state, which describes no particles. And then obviously also state that describes some particles, but vacuum is kind of fundamental starting point. So they have this construction of a functor that satisfies those axioms, but no prescription or no construction of a vacuum state in general. Okay, so more recently, kind of right now, Frenhagen and two of this bunch, so Brunetti, Ditch, and myself, we are actually, well, I don't want to say too much, but I think we have a construction of the generalization of that model to gauge theories. So this is work in progress, hopefully out soon. So out soon, and by Brunetti, Ditch, Frenhagen, myself. So we have this generalization to not all gauge theories, but gauge theories where you can gauge fix explicitly to gauge theories with gauge fixing. So not like super beautiful, but working. And again, the same caveat, no vacuum state. No vacuum state. And that last caveat means that, although I would love to, we are not going to claim that Millennium Prize, because if you want, just for the record, you also need to construct a state, because otherwise that mass gap situation is not going to solve itself. But yeah, I think what I want to stress is that there are ways to construct these models in the original sister algebraic framework, at least on the level of a factor. So that is maybe worth looking at. Now, but the question of states is important, and it kind of motivates to keep on working on the other approaches. So for the rest of this talk, I want to focus on this particular setting. So if you want to have a framework which comes with a sort of vacuum state for free, and you can compute things, and it's very sort of practical in the same sense of, you know, connection to what physicists actually compute, well, this one is your friend. But the caveat is that it's perturbative. So you work with chain complexes, you work with formal power series in H bar. So it's not as beautiful functional analytically, but it's beautiful in other ways. Okay.
So
yes.
Just to
Yes.
make sure I understand. So you say that like if you take like C star algebras or these topological star algebras as target, it's hard to produce states, or you have
Yeah.
theorems that tell you there can't be.
No, we
states?
don't have a theorem. Well, if we had a theorem telling that there are no vacuum states for this, that would actually be very cool. It would annoy the hell out of everyone, but it would be great. It would mean that quantum field theory as we know it doesn't make sense officially. But so it's a sort of like, if you want to set fire to your whole work of your career, do that. No, we don't have a proof that things don't exist, but we also have no constructive method. Well, we also don't have a proof that they exist. Okay, so we don't have either. It's a kind of open problem this way or the other. We can construct states explicitly for free theories, but everybody can. So yeah, this is a non-trivial question. Yes.
Maybe elaborate on what it means to generalize to gauge theories. Can you construct them? Can you?
Yeah. So take, say, Young-Mills. Okay. So you say Young-Mills. I give you that factor. Okay. So gauge theories where you have explicit gauge fixing. So yeah, you say QED, I give you that factor, or the standard model. So like the you know, the kind of simple guys where you can, in a sense, reduce things to that case just with more fields. It's not entirely trivial to do this. That's why we haven't done it like 4 years ago, but it's similar in spirit. There was another question. Yes.
Sorry, I might have missed this, but could you say what a vacuum state is supposed to mean?
Yeah, I can to an extent. So in the traditional QFT, it's so traditional QFT is on Minkowski spacetime, and a state is what it is, right? And then you're looking for states that are invariant under the isometry class of your spacetime, so invariant under all the Poincare transformation. So that's what the vacuum state is on Minkowski. It's the state that's invariant under Poincare transformation, and sort of physically it means there is nothing there's like literally nothing, right? But there are generalizations of that notion also to curved spacetime. So there's a class of states that behave like the vacuum. So it's kind of, yeah, it's actually it's a good point. What is a vacuum state? But at least on Minkowski, I think people have a good idea of what this is supposed to be. So when they find it, they know it. Yes.
So we're saying that there's no constructions of vacuum states. Do we mean that there's no global like vacuums for these things on the left board, or do we mean just like locally no vacuums?
Well, either way. So what this construction gives you is a functor, right? So well, yeah, I mean, obviously you want to construct the vacuum on the whole algebra, but even locally, we don't really know. So it's actually, yeah, so this construction here is actually very algebraic. I'm going to give it at the end of the talk. You can understand it like 2 minutes. But the question about the existence of states, it's a hard function analysis problem. Unless somebody comes with a brilliant idea that simplifies it to something that is easier. But yeah, you cannot then avoid your functional analysis yet. Okay, very good. Any more questions? Great, so if not, then I'm going to say a bit about that, and then I will come back to these models. Because that whole approach was very strongly inspired by results from PAQFT. So these two are PAQFT. So it's not a coincidence that the same people are working on these. All right, so let's get started. So models in PAQFT. Okay, so we have our manifold, and I'm going to present you construction of models for the scalar field. I know this is boring, but I mean, this is somewhat simpler, and then I will tell you what to do more general stuff. So, yeah, so first the space of fields, classical fields. I will call it configuration space. This is smooth functions on M. And then I consider observables, classical observables that are functions of fields. So in particular, they're local functionals on E. So these are denoted F loc. And an element here, F is of the following form. So F of phi is in E, is an integral over the whole M of some function of the finite jet of phi. Okay, so this is local because it only depends on the finite jet. And then, well, these don't form an algebra in an obvious way because multiplication of functionals looks like this. So multiplication, so F times G for two functionals of phi, multiplying these things pointwise. That is F of phi times G of phi. These are local. This doesn't have to be local. It's at best bilocal. So we can consider a sort of algebraic completion of local functionals under this multiplication. So F is multilocal functionals So this is completion, algebraic completion of F block under dot. Okay, so that's sort of main players of the theory that I want to build those algebras from, but I need some algebraic structure. This is given in terms of dynamics, and dynamics, well, I guess, so Michele was talking about Hamiltonian framework. I'm going to use Lagrangian framework, which is not too far off. So dynamics will be given in terms of variation of a Lagrangian. So Lagrangian is also, well, something like a functional, it's a bit more subtle, but the variation of a functional is essentially a one form on this space of configurations. So dynamics given in terms of a one form ds. So one form, well, actually, I can write explicitly. So it's one form on the configuration space. And the equations of motion they are simply stated that a solution is in the zero locus of this form. So then phi is a solution. Okay. All right, yes? Is an element of this space. It's a function. Smooth. I don't know what kind of objects are smooth functions. Yes.
I can't parse with D as fine.
Oh, okay. So yeah, I mean it's a one form at point phi. So you evaluate, you take the yeah.
Okay.
Yeah. It phi is a point on.
So you want this whole vector to vanish. Yeah, okay.
Well, it's a kind of more of a covector, but yes. Yes. Yeah, then that covector vanishes identically. Yes, please.
I guess it generalizes in an obvious way to more complex configuration spaces.
Absolutely, yes. I mean, it generalizes also to like graded things as well, which is the gauge theories context. Yeah. So this is like just a basic like, geometry thing. Yeah. So and with that, I want to now consider the space of well, these guys, multilocal functionals on the solution space. So let's write this phi in ES. Sorry, that's an S, it's very ugly. So now functionals, maybe multilocal functionals on solution space. So I want to characterize them algebraically. So I define them as a quotient. So all the functionals modulo things that vanish on solution space. So F0 functionals that vanish on F0, and now the question is how to characterize on E0 or ES. How to characterize F0. And the sort of natural way to do it is using vector fields. So by the this is a one form, right? So if we pair it with a vector field, we get a function, and by definition, that function is going to vanish on solution space, right? Because this one form vanishes on solution space. So remark that if X is any vector field, then if I insert this ds into X, well, not any vector field, any vector field that's also multi-local. Okay, so it has to satisfy those sort of regularity conditions. Yeah. Then the pairing of that vector field is in F0. So now a fact, which is actually proven. So fact, and this is, I guess, okay, so it's a paper that is now on the archive, but I don't remember the number. But the combination of authors is unique. So Hawkins, Visser, who is Eli Hawkins' PhD student, great guy, graduating soon, and myself, actually, yeah, 2023. F0, so all the elements of F0 or the scalar field are of, let's give it a label, of the form star. So that procedure of contracting with one for completely characterizes F0, and that suggests a very nice way of characterizing Fs in a homological way. Let me add that this paper is, I mean, okay, in a sense, it's kind of obvious what one should do, but the paper is highly non-obvious because there are many functional analytic traps along the way. So the reason why it was done like last year and not like 20 years ago, it's because there was a fact about functional analysis and infinite dimensional spaces that people have missed for like 20 years. So although it's all fun and relatively easy to formulate, some of these things are a bit of a minefield. But I will not talk about those things. All right, but with that established, we are happy to go back to more algebraic things and say the following. So let's take the space of all multi-vector fields. So let's see. So multi-vector, no, multi-local multi-vector fields. Sorry, this is a mouthful. Multi-local multi-vector fields. Okay, so yeah, this is an exterior algebra over vector fields that are multi-local. So this is the notation. And then take that, define differential delta S by extending this insertion of the S and get the chain complex delta S. And by definition, H0 of that, well, what is it? Let's check. So here we have 0 order using the negative grading because reasons, -2, and so on. So we are looking here. The kernel of this map is all of F. The image of this map, this is delta S. The image of this map by that nice little result is at 0 and 0. So this is Fs. Okay, done. So this construction is well, essentially giving you a homological interpretation of the space of functionals on the solution space. Yeah, so that is already the chain complexes part of this
Are the
construction.
other homology groups all 0?
No, that depends on the theory. I mean, for sort of, well, for the free scalar field, yes. But if you include gauge theories or if you include anything with local symmetries, then no. So H1 is telling you about symmetries. So then you do more interesting stuff. Okay, but this still doesn't have all the algebraic structures, so it has a differential. But there is also, well, in algebras there is also a product. So here I have the pointwise product. In classical theory, I would also add to this a Poisson bracket, kind of maybe along the lines of what Michele was saying. And for quantum theory, I want a product which is, however, non-commutative. Commutative products are not very good for quantum theory. So there is more to be done. So let's see. So I'm not going to do it yet because I want to quickly go back to this more abstract construction of models. So how do I characterize dynamics in this C-star algebraic setting? So maybe the first thing I can actually very quickly tell you what that factor is, and then explain how it connects to the story I already presented. So C-star algebraic framework. Okay, so this is kind of top down. So this guy is going bottom up. We're now going top down and hopefully meet in the middle. So we are taking an algebra, C-star algebra, which is generated by a prescribed family of unitaries. So that's an old trick, right? Take a free algebra generated by blah, blah, blah. Everybody knows how to do that. So here, these local functionals I mentioned before, they will act as potential interactions, potential observables in the game. So this is going to be the C-star algebra generated. Okay, so maybe I should, which part of it is the business part? This one, okay. Okay. So let's fix M and fix a Lagrangian L. Okay, so I said something about Lagrangians not being obviously functionals. This is related to the fact that, well, ideally a Lagrangian should be an integral of the Lagrangian density over a whole manifold. Now, M is non-compact. So if you take your favorite Lagrangian density from a physics textbook and integrate it over a non-compact manifold, in general, you know, for phi's that are not compactly supported, for fields that can have whatever follow-up conditions, that's a bad idea because you get something which doesn't necessarily converge. So in this framework, a Lagrangian is coming with some sort of a cutoff. So what is it? So L is a map from the space of test functions, so smooth, compactly supported functions on M to local functionals. So, for example, you get the Lagrangian for the free scalar field, which is 1/2 minus, oh, where is the minus here or there? Oh, well, yeah, one of them. I guess the sign doesn't matter that much. Plus m squared I squared. And here I'm just multiplying it with f and add some integration measure. Okay, so this f is kind of providing a cutoff. And then with this Lagrangian, I can tell you how to get that one form here. So you can consider a variation. So let psi be a compactly supported field. So you define a variation of L in the direction of psi. This is defined as L of f. Actually, sorry, need one more argument of phi. So this is L of f for shifted phi. Okay, so I'm shifting it by a certain compactly supported minus the original one. Okay. And for future convenience, let me introduce a notation. Okay, so f psi of phi, this is a functional, f is in f log is defined as f at this shifted argument. Okay, so that's a variation. And now from variation to derivative, that's not very far. So then dl, sorry, I've been using the notation S, but maybe I should be using L. It's just the notation changes between papers. So this is limit t going to 0, 1 over t, and then dl of t psi. Okay, so this is just, this defines a sort of finite variation, and this defines the first derivative. So this object here, A is independent of the choice of that cutoff because locality. B, it's a sort of finite version of this one form that we discussed earlier. So here is how the dynamics is connected, and this object is going to enter that formulation. Okay, so I'm going to do strategy. So now I can formulate the axioms. So A, not axioms, sorry, well, yeah, relations. So A, M, A, L, factor from cos M to C star alg is defined as follows. So AL of M is C star algebra generated by a family of unitaries S of F, where F are local functionals, such that, so with relations, and there are two relations. So one relation is related to causality. So if I have F plus G plus H, such that the support of F is later, actually I should say not earlier than support H. So in other words, here is F and H is here. So it's so I said not earlier because it can be either in the past, this is in the past, or space-like to F. Then S of that factorizes to S of F plus G times S of G to the minus 1 times SG plus H. So that's causality.
So that means that there are no backward pointing causal curves from the support of H to the support of F. Is that right?
Yes, that is correct. That is exactly correct. And then the second one is the dynamics. And that will use that delta L object I introduced before. So if I have S of now shifted F plus delta L of psi, this is equal to S of delta L of psi to the minus 1 times S of F, and also from the other side. Okay, so that's dynamics. And it's not entirely obvious what that is, I'm sorry about that. But if you are familiar with some quantum field theory, this is a sort of unitary version of something called the Schwinger-Dyson equation of Schwinger-Dyson equation. Okay. So two basic relations. So then if you want to get more stuff, you require more relations, but I'm not going to talk about it at the moment. What I want to say is, well, how to think about those objects S of F. So obviously from an abstract perspective, it doesn't matter. Okay, this is my algebra, I defined it, you go and do something with it. But they are motivated A by physics, B by this PAQFT approach. So going back, so in PAQFT, so then S of F, these things are formal S matrices. Okay, and what they are, they're actually constructed using a product that I introduced. It's still there. I introduced here on this complex. So it already comes with a certain product, but I deform the product that exists here, the pointwise product, to a new product. Yeah.
Can you say, like, how do you get a star norm?
I can tell you later. It's actually a standard construction. Yeah, I will.
So there's
give you.
a unique star norm, is
Yeah. That's a canonical thing. I mean, by definition, you have, it's a group C-star algebra for that group of unitaries. So, but yeah, I will give you a reference later. Okay, so there is, so on this space, I introduce a new product called T. This is time-ordered product. So this is a deformation of the pointwise product, and almost there. And define S of F as a time-ordered exponential of I over H bar F. Okay, so these abstract objects from abstract unitaries from the C-star algebraic perspective can be realized as some concrete, well, unitary-ish objects in this perturbative framework. One more thing. So here, again, from a sort of this graded algebra perspective, so I had, just to summarize, I had initially sort of this algebra with the pointwise product, the classical product, then there is some sort of deformation called T, and then and here I had the classical differential, okay, and then that goes to, so either you deform the product and leave the differential as is, or, okay, good, or you leave the product as is, and you deform the differential. D hat S is T minus 1 composed with ds composed with T. And this guy you might be familiar with is the quantum BV differential. So given in terms of the BV Laplacian. Okay, so this kind of connects that framework also to the works of Kevin and Owen using factorization algebras, where they essentially work with the formation of the differential. Okay, so yeah, I hope I gave you some sort of idea of how to construct things in QFT. As I said, the gauge theories part for that C-star algebraic framework is coming. It should be coming soon after I finish the paper with Michele, then I finish the paper on that. And yeah, that's all I wanted to say. Thank you.
Questions, comments?
Yes.
To me, where do the chain complexes and like you said, do you need chain complexes in this perturbative expression?
Yes, that's a chain complex.
That's there.
That's a chain complex.
But over here in the quantized setting, so to speak.
Also, I mean, these are, yeah, so this is the PQFT quantized version. So this is the classical theory, and this is the quantum theory. So the quantization is through the formation of this product, or through the formation of this differential. So that's how, yeah.
Okay, so in relation to that, sorry,
Yeah.
I was wondering how
Yeah.
this is just a finite dimensional case. If I
Yes.
just have a manifold with a one form.
Yeah,
And look at this
Yeah.
complex,
Yeah.
what do I see then? What's the outcome?
well, the space of solutions to your equations, I mean, this is like known stuff. These are like
Like,
puzzle
I-
complexes. I mean, this has been done for finite dimensional manifolds as well. Like, this is the way of characterizing a zero locus of one form.
Yeah, exactly.
Potentially.
What are the higher groups? Like what are the?
Oh, we can compute it, right? So I mean, the first, yeah, H minus one characterizes the symmetries of the equations of motion, right? Because these are, if we look at this, right? So these would be things that are mapped to the, well, so this is the kernel of delta S, right? Modulo the image of delta S. So what's kernel of delta S? Let me show you. So I think it's also educational to see it. So here, per delta S. So these are vector fields such that if I insert ds, this is identically zero. So these vector fields can be thought of as symmetries of the action. So identically zero, not zero onshore, right? Symmetries of the action, or the Lagrangian S. So this is interesting. And obviously this is how you detect gauge symmetries, because they are in H minus one. And then physicists typically want to kill off those symmetries by adding something in degree minus two. So that has a good reason. But yeah, but you know, mathematically you can just go off and compute. And yeah, it's definitely well, that's something that people have been doing, I guess.
I was wondering, so
Yeah.
this theory that you're describing at the end, is that based on this Lagrangian of the free field theory?
Yes, so here S would be, yeah, so this is the free Lagrange, yeah, so S is the free action.
We're talking about the quantization of the
Free,
field.
however, yeah, so the point of introducing these S matrices is that these F's characterize interactions. So S is the free action, F is the interaction. So using these objects, you can actually construct interacting fields, Kasia matrices, and so on. So it's perturbative in the sense that you're starting with free theory and then like modeling sort of interaction using, well, further deforming the free theory. So
Somebody very outside the field might test of whether it's free or not is whether I see Feynman diagrams during the talk. I didn't see any Feynman diagrams. So they're sort of hidden in that exponential there.
yeah. So T, okay, physicist speech now. So T is what? So it's H bar, and now yeah. So here I have the Feynman propagator, and here I have derivatives. Okay, and now I apply it to say if F is phi to the 4, then F is represented as a sort of 4 vertex. So when I compute this, I'm contracting, you know, the powers of this vertex with these copies of the Feynman propagator. So this is full of Feynman diagrams, a lot. So yeah, they're there.
Any other questions?
Yes.
This response is also on that blackboard understanding. So all the products are commutative.
Yes, all the products are commutative.
So what does this non-commutative product appear that is?
Good question. I like your question. Yes. So from this from this commutative product, assuming the time slice axiom, you can actually reconstruct a non-commutative, well, maybe I should say the non-commutative product from the C-star algebraic settings. So there is a reconstruction procedure. And this was a paper of Owen, William, and myself from, I don't know, 2019 maybe. So from this, you can reconstruct a non-commutative product. But so what you usually use, but it's something like, yeah, so this time slice axiom means that say factorization algebra language, your factorization algebra would be locally constant in time. And then from a locally constant data, you can reconstruct an associative non-commutative product. So in one dimension, it's very easy. If you do it in one dimension, you can easily see you have an associative algebra. This is the same, but you have additional dimensions, but they don't matter. So yeah, that already hides information about the star product.
All right, let's thank Kasia again. So at 2 o'clock, we'll have a series of shorter talks. We have that for you.
Yeah, I should give you the reference. So